Hi, welcome. Today we will be talking a little bit about the quantum mechanical point of view, or the models or the way we understand solids from the quantum mechanical point of view. So this is going to be a very technical session. So we'll basically do the demonstration of what is called the Blochs theorem. And after that, in the next session, then we will give physical meaning to all the things that will come out today, which will seem very, very mathematical and very technical. So please bear with me and keep in mind that in the next section we will build an intuition and a relationship between the things that will come up today and the actual crystals and how crystals are understood from this perspective. So let's get started. First things first. What is what we call a solid? And that is a question that is a little bit tricky. If you ask probably a high school student, would tell you that a solid is something that is hard, and that there are three states of matter: liquids, gases, and solids, which is not entirely true. And if you ask them, for example, if a piece of wood had to be classified in these three possible states of matter, probably a piece of wood would be classified as a solid, or a piece of glass, the glass in a window in the room that you are probably standing right now, it's would probably classify in this intuitive way as a solid. And many other things that are around us, even, I mean, ourselves, our skin or our bones, do they classify as a solid or as a gas or as a liquid? And the answer is no, that is not. All of these examples that I just gave are actually not solids. Solids from the physical point of view are materials that have a periodic arrangement of their atoms. So this means that the atoms or the molecules or whatever the material is made of will be arranged in a periodic way. And from these, I mean, what we understand by this is that, for example, the atoms or these dots I'm drawing there on the screen, could be atoms or molecules or anything, are arranged in a periodic way. And this periodic way could be, for example, a square lattice like the one I'm showing there, or it could be some other form of lattice, for example this one that has its atoms offset from one layer to the next, so something that looks like that, and so on and so forth. So there are many ways of arranging atoms periodically, but the most important thing is that solids, what we call solids in physics, are materials that have their atoms arranged in a periodic fashion, in repeatable patterns over space. And this is not the case for glass. For example, the glass of the windows is actually a disorganized arrangement of silicon oxide molecules. So you have silicon oxide molecules that when they cool down, I mean, you can melt them and turn them into a liquid. When they cool down, when this thing freezes or gets hard, actually does not form a periodic arrangement of these molecules. The molecules basically just get stuck in the positions where they are, but they are not, they are in random orientations or random positions in this glassy form, which we call a glass or a super cooled liquid, some people call it as well. But the main thing is the atoms or the molecules are not arranged in a periodic, organized, ordered arrangement in the space. The same applies to several other materials. I mean, wood, for example. Wood, although it has some sort of arrangement in the way molecules and basically sugars are arranged. It's not a nicely periodic arrangement. So again, this material is not a solid. So examples of solids are quartz, for example. Quartz that you get in mines that has grown under very particular conditions is silicon oxide as well. So similar to the glasses from windows, but in that case, the quartz has an organized three-dimensional arrangement of atoms that follows a very particular pattern, and this gives very different optical and electrical and thermal properties to what we call crystalline quartz in comparison to glassy quartz, which is the normal glass that we use for windows or optical elements or other things. So there are many other crystalline materials. For example, silicon, germanium, gallium arsenide are all examples of certain types of solids that we call semiconductors. There are many other insulators. There are many minerals that form crystals, pyrite, for example, and so on and so forth. So so let's go into a little bit more detail into this idea of having a three-dimensional periodic arrangement of atoms. Making three-dimensional drawings is very difficult, so here we will just make two-dimensional arrangements and so on, but bear in mind that we're always thinking of three-dimensional arrangements. So we will move to a concept that is very important and will be very important for us in the coming sessions. That is the concept of lattice. This is a mathematical concept. Let's forget for a moment about atoms or molecules or physical components. Let's just think mathematically. So if you have a three-dimensional arrangement of points, that's what we call a lattice, a periodic three-dimensional arrangement of points, mathematical abstract points. And a lattice can be generated, we call these the generating vectors or the base vectors of a lattice by defining vectors of a given size. They don't have to be unit vectors. They could have any magnitude, but defining vectors that could be orthogonal or not orthogonal that translate a point of the lattice, let's say for example this point here, to the next neighbors of the lattice. So if we apply, for example, this A vector here, this will bring us to the next neighbor in the lattice. Or we can also apply the B vector to this atom, and this will bring us to this next neighbor in the lattice. We could apply -1 times A, and this will bring us to the other side, the first neighbor in the other direction. And of course we can apply -B, and this will bring us to the next neighbor in the lattice. And again, I'm just drawing here a square lattice for simplicity, but it could be a more complicated one. But the idea is that we have these base vectors that form a base that any integer translation, we call it. So if we multiply these vectors, and here I'm putting the equation in three-dimensional, so we have a base vector in the x direction, in the y direction, in the z direction, if it's a square lattice. If not, they could be vectors that form other strange angles that are not 90 degrees. That's still okay. We can form lattices in those cases as well. But the most important thing here is that if you multiply these three vectors by integer numbers, so 33 times A minus 2 times B and plus 7 times C, this will be called what we call, this will be what we call an integer translation. So this brings one point of the lattice, let's say this point here, if we move it, I don't know, 4 times in the direction of A, 4 integer times in the direction of A, and 3 times, the 3 times in the direction of A and 2 times in the direction of B, for example, this will bring us to this point, which is also a point in the lattice. So integer translations are vectors that take one point of the lattice to another point in the lattice, and they can be represented as linear combinations with integer coefficients of the base vectors of the lattice. Okay, this is more or less what I want you to bear in mind. It so happens that there were people, among them a guy whose surname was Bravais, who studied these from the mathematical point of view. I will write down the name here. Bravais, who is a French name, I believe. What Bravais realized is that there are actually 14 different ways of arranging atoms in a three-dimensional space, or points in a three-dimensional space. So we're talking now of abstract points. Periodic arrangements of atoms in 3 dimensions can be classified in what he called lattices, or 14 types of lattices that we know now as the Bravais lattices. Okay, all the things that are related with how lattices are arranged and which ones are the types and the names of all these Bravais lattices and so on, you can find in a separate lecture that is not mine. I'm recommending it here in the comments for this video. Please have a look at them. They are very short videos. There are about 7 or 8 different very short videos in which they explain very clearly with very nice 3-dimensional graphics or 2-dimensional graphics, but they explain really nicely the way Bravais lattices are built and why there are only 14 of them, and so on and so forth, and what's the difference between all of them, and so on. So please do have a look at that, at those videos. It's a very, very nice course, and if you want, in order to understand more about the symmetries and the way we can arrange atoms periodically in 3-dimensional space. And we will in the future, during the coming few sessions, probably use some of the concepts that are discussed in detail there in this other course. So please do have a look at the videos. But for the moment, we will jump in straight onto the demonstration of the Bloch's theorem. So here I wrote what is the Bloch's theorem. So you have a Schrödinger equation at the top, a Hamiltonian times wave function, which then I wrote explicitly, which can be written as the momentum operator here, plus u of r, where u of r is actually the potential. And we changed the v that we traditionally use for u to be very clear and denote that this u is a periodic potential. So I will come into that, or why we put a periodic potential in a second. Applied on the wave function, it gives us an energy, which I depict here with a curvy E times the wave function. And the Bloch's theorem says the eigenfunctions and eigenvalues of the Hamiltonian of a potential where u, the potential, of certain position r, any r, is equal to u of r plus a capital R for all capital R's in the Bravais lattice. This means if we have an integer translation, just like the ones I showed earlier, the solution for these are plane waves multiplied by a function with the periodicity of the lattice. And this is what is depicted in the equation below. So the wave function that results from solving this Hamiltonian will have to be a plane wave. This is a plane wave multiplied by a function where this function u is actually has the same periodicity than the potential. So this doesn't mean it has the same shape. It can have a different shape, but the thing is, if the potential repeats every, let's say, angstrom, or every 10 angstroms, or every 100 angstroms, the periodic potential U will also repeat over the same period, and that's what this means. And why would we have a periodic potential? Well, okay, the Bloch's theorem deals with what we call Bloch's electrons, and Bloch's electrons are basically the quantum mechanical version of the Drude electrons that we discussed in the previous session. So these are electrons that don't interact with each other, so there is no interaction. Two electrons in the material do not interact with each other, they don't see each other, and basically the only interaction they have is with the nuclei in the lattice, basically in the material. So if we think, and let me put here just one-dimensional periodic arrangement of atoms. Let's think this is the nuclei, so they are positively charged, and if we want to draw the potential energy due to this periodic arrangement, and this is very important, the periodic arrangement is in principle infinite. So you have, this is not, I'm drawing here just 6 atoms, but it's actually an infinite chain in both directions of atoms. And what would the potential look like for this set of atoms or set of nuclei? So again, thinking just in terms of, for example, hydrogen atoms or something very simple, just positively charged dots arrayed at periodic distances will mean that very close to the in the vicinity here of one of the atoms, for example, what the electron will feel should be something very similar to a hydrogen atom or just a Coulomb potential. So the potential here will have an asymptote or a singularity, and then it will start going back to, let's say, a 0 level, but then the interaction with the next atom will start being stronger, so you will have a potential that looks like that, right? And if the potential or the only interaction that the electrons see is the Coulomb potential due to this periodic arrangement of nuclei, this means that the potential is actually a periodic function. So the function of the potential, which I try to draw there in blue, will have this period, and this means that this potential is repeatable. It looks the same over this period and over this period and over this period and so on and so forth. So that's why Bloch electrons and the Bloch theorem deals with periodic potentials. So we want to see what are the solutions for the energy levels of an electron that is immersed in this kind of potential. Remember that in a real crystal it's not just a one-dimensional arrangement or a two-dimensional arrangement, but it's actually a three-dimensional arrangement of atoms. So this is a very simplistic scheme of the idea that we want to translate into 3 dimensions. Okay, but the idea is I think is very clear from this drawing, and why the potential U here, this is U of R, will have to be a periodic a periodic function like the one we are seeing over here. Okay, so moving on from here, we have to now try to demonstrate this theorem. Let's do that. Let's define TR. TR will be an operator related to the vector r, where r is an integer translation through the lattice. This means it's an integer number of times the vector a, an integer number of times the vector b, and an integer number of vectors integer number of times the vector c. So this is again a translation in the lattice. And t, the operator t, is an operator such that it doesn't matter which function you put in front of it. If you take t of r, t sub r, and you apply it to a function, let's say a function f of r, the result of applying this operator on the function r will be translating the function by r. So it will be f of r plus capital R. Okay? So, right. This operator is basically an operator that when it operates on some function, it basically just translates the argument by the integer translation r. Okay, great. Given that the Hamiltonian, you remember, I'm going back to here. The Hamiltonian here, the first part doesn't have any dependence on the position, and the second part here only has a dependence on the position. But since this function u is actually periodic, what we will see is that that if we apply if we apply t sub r on the Hamiltonian operator, which we then apply on a function which will be the wave function, for example, what this does is it, let's say we organize it like this. So the operator changes the argument of everything that is in front of it. So since the Hamiltonian is actually periodic, I'll just write this explicitly: r plus r and psi of r plus r. Okay, so since the Hamiltonian is periodic, evaluating it in r or evaluating it in r plus capital R is the same. So you go back to the Hamiltonian evaluated in r times the wave function evaluated in r plus r. Okay, and this means that this can be rewritten as h of r applied on t sub r applied on the wave function, the wave function of r. And what we demonstrated here is that actually Hamiltonian applied on t sub r applied on psi. So this means that the Hamiltonian and the translation operator t sub r commute. And that has very important, if you recall from our previous lectures, this has very important implications, because if t sub r applied on the Hamiltonian is the same as the Hamiltonian applied on t sub r, this means that these two operators share the same set of eigenfunctions. Not the same set of eigenvalues, but the same set of eigenfunctions. And that's something very, very important that we will benefit from in the next few steps. Let's say we take the operator we had, t sub r, and we take one other operator, now t sub r prime. So we have t sub r prime. That's an operator that does exactly the same, but just is a different translation. Maybe one translation is 3 times in the A direction and 2 times in the B direction, and the other one is, I don't know, 10 times in the A direction and minus 3 times in the B direction, or something like that. I mean, it's just any two integer translations, and these are the operators that relate to those two particular integer translations. So if we apply these on the wave function of R, what we obtain is basically that this is equal to T sub R applied on psi of R plus R prime, which is equal to psi on R plus R prime plus R, and this is equal to psi on R plus R prime. That's just because there is commutation between vectors, and these can be rewritten as T sub R prime of psi R plus R, which is equal to T of R prime T sub R on psi of R. Okay, and this has two. Well, this is also important because the two translation operators commute with each other as well. But one thing that is even more important, if we take this step right here, we can also follow from there. This is equal to T sub R plus R prime. So this means that this is also equal, the application of the two operators is also equivalent to another operator, which is the operator of the addition of the two translations. Okay, so okay, great. Now, since we already said the Hamiltonian and the translation operators commute with each other, this means that they share the same set of eigenfunctions, and therefore we can write something that looks like this. So the Hamiltonian applied on the wave function will be equal to the energy times the same wave function. However, T sub R applied on the wave function will also be an eigenfunction of the translation operator, and these we will call C sub R psi. So this is the eigenvalue for the translation operator for this wave function, and E is the eigenvalue for the Hamiltonian in this case. Okay, so right now let's try to see what happens there. So right, let's apply the two translation operators one after the other on the wave function. So we have T sub R T R prime on psi. This will be equal to C of R T sub R prime of psi, which will be equal to C sub r C sub r prime psi of r. Okay, so from these we obtain also from the previous demonstration, this is also equal to T r plus r prime applied on psi, which is equal to C of r plus r prime. Okay, again, this is all very mathematical, very abstract, but what we demonstrated here is that the multiplication of these two eigenvalues that correspond to the individual translation operators are the same as the eigenvalue that corresponds to the operator of the addition of the two translations. Okay, so in other words, what we get is that C of r plus r prime is equal to C of r C of r prime. Okay, great. So let's now go one more step. Let's say that AI are the base vectors of the lattice. So if we have the lattice here, again I'm just drawing it two-dimensionally, and the cubic or square lattice for simplicity, but it could be any lattice. We can put A1 here and, for example, A2 here, and in principle we would have A3 coming out of the plane of the screen. Okay, so let's call them A1, A2, and A3, the three vectors that that translate the unit vectors of the lattice, that translate one point to the next one in the three directions of the Bravais lattice. So these are what we call the primitive vectors of the lattice. Okay, great. So 1 times A1 plus 0 times A2 plus 0 times A3, so that means the translation that is just move one place of the lattice in one direction and that's it, is also an integer translation. So in particular it will have an eigenvalue for the translation for its translation operator. So let's see. So the C, let me just be consistent with the colors. So the eigenvalue of AI, we will write that in the form e to the 2 pi I psi I. Okay. We can always choose a psi I such that this is true. We can choose a psi I that is a complex number that will give you any number that C is. So this C of I, we can always find a psi I value such that when we put it in the exponent of this exponential, will give you whatever value it is. So we're writing this eigenvalue in this particular form because it will make our lives easier in the following steps. Okay. Now, as we said, these are the AI are the base vectors of the lattice, or the primitive vectors of the lattice, and each one of them will have its own eigenvalue for the translation operator that corresponds to this particular just unitary translation in one of the directions of the lattice. Okay, so any translation, any arbitrary integer translation, we said, can be written as n1 a1 plus n2 a2 plus n3 a3. Okay, and using combining all the results we've put together in the last couple of slides, what we can see is that the eigenvalue of the translation that corresponds to this arbitrary integer translation will be the product of breaking it into small pieces, and we can write as the eigenvalue of a1 to the n1 times the eigenvalue of a2 to the n2 times the eigenvalue of a3 to the n3. Okay, so and these we can also rewrite as C of r equal e to the I k dot r, where k is equal to psi1 times a1 plus psi2 times a2 plus psi3 times a3. Okay, where these three capital A vectors are what we call the unit vectors or the primitive vectors of the reciprocal lattice. And we will discuss a little bit more about that in a minute. The main point here is that I want to show you that in principle this is possible. So it's just a relatively complicated, or it's actually a very simplified way of writing this complicated number that we will then use. Okay, but the thing is, this k vector here emerges like this, where the capital A's are things that we still have to define, and we will do that in just a second. Okay, so now the translation operator for r applied on psi of r will be equal to psi of r plus r, and this will be equal to e to the I k dot r psi of r. Just combining all the ideas that we've put together in the last previous slide. So if you recall, the eigen so these translation operators are have the wave functions of the Hamiltonian as eigenfunctions. When we apply this translation operator on a wave function, it translates it, but it also happens that it produces an eigenvalue, which is this one, which we can write like this, and which we can put in here, just as we've done so far in other cases of quantum mechanical operators. Again, this is very technical, very mathematical. We haven't done anything with physics. We don't really understand what this is yet, but we will in the following steps. So just bear with me for a second. The most important part here to bear in mind is that this part here, this part here, implies that I will continue just here before we move on to the next slide. That the wave function psi, which I will already put these indices in, has to be of the form e to the I k dot r plus u of nk of r, sorry, r, um, um, and this is just because that's the only way this can comply with this thing here. So from these, what we have shown is that this function here has to be a periodic function, and so the wave function has to be the product of a periodic function with the periodicity of the lattice times this function over here, which so happens to be a wave, a plane wave in 3 dimensions. Okay, so let's now carry on trying to give a little bit of meaning to these capital A vectors and what they are and how they, where they come from. Okay, so let's assume now that we have a real crystal lattice. What does this mean? A mathematical lattice, as we said, is an infinite in all 3 direction arrangement of periodic arrangement of points. A real crystal, if you think of a piece of silicon or a piece of quartz or any other material that you can think of, it's actually not infinite. It has a very, very large number of atoms, especially if it's a macroscopic crystal. So if it's a chunk, a big piece of let's say quartz or silicon or whatever, the number of atoms there, it's going to be very, very large. I mean, we're talking about Avogadro's number type of large. So we're talking about 10 to the 23 or so. I'm putting here, the Avogadro's number, which is the number of atoms that there are in a mole of some material. So the number of atoms that will be involved in a real macroscopic piece of any crystal is going to be large. It's not going to be infinite, but it's going to be a very, very large number. So in that sense, now we have to deal with this part. The fact that the number of atoms is actually not infinite, is a finite, large, very large, but finite number. Okay, so what happens, let's say that you have your crystal. And again, I'm going to draw here a very quick square lattice. Let's say you have many repetition cycles in between, but eventually you have reached, again, this is a real crystal, so let's say this is the first layer of atoms. So you have your crystal, you have one first layer of atoms here, then the rest of the crystal, hundreds, millions and millions and millions of atoms over the course of, let's say, a centimeter or a meter or whatever the size of your crystal is, and then eventually you reach the last layer of the crystal. So let's assume that we're going from the first to the last layer of the crystal, and let's see how many lattice sites are there to move from, let's say, this point to this other point. So moving from here to here implies going through a really large number of lattice sites. And again, but it's not infinite, it's finite. So let's call the number of lattice sites in your real crystal N1, N2, and N3. So what we will have is that N, the total number of atoms in your crystal, in your bulky crystal, is going to be N1 times N2 times N3, where N1 is the number of lattice sites in one direction. N2 will be the number of lattice sites in the other direction, and N3 is going to be the number of lattice sites in the third direction. Okay, great, and we know that this number N, capital L, N, so this one, is going to be a large number of the order of Avogadro's number. It could be 1 mole or 10 moles or 100 moles of material, but it's going to be of the order of 10 to the 23 or so. So each one of the n1, n2, and n3 will be of the order of the square root of these, which is still a pretty big number. We're talking about 10 to the 8 or so. And again, it could be more or less depending on the actual number of atoms, or if the crystal could be much longer in one direction than in the other, and so on. But again, we're not talking about the actual number. We're talking just about of the order of magnitude. Is this very large number of sites. Okay, so great. So what happens if, for example, we take the potential somewhere here in the first layer of lattices? So if we look at the potential somewhere in this region here, near one edge of the crystal, and then we look into the potential somewhere here on the other edge of the potential. Of course, if you go in the middle and you have hundreds or millions of sites in every direction, everything looks like if it was an infinite. So if I'm standing somewhere around here in the center of the crystal, you have millions of sites up, down, left, right, and in all three directions. So in that case, the lattice looks just like an infinite lattice. But if you're standing near the edge, and let's say we move from the first site, we take a position somewhere in this site, and we move the number of sites that take us to the other edge, this will bring us to the same position here in this last site, right? So the function or the wave function in the position R, which is the initial position, is this position right here, plus n I a I. So this is translating all the way through to the other end of the crystal. We have to assume that these two are the same. Why? Because you are in one edge of the crystal and you are in the other edge of the crystal, and apart from the fact that you have free space on the left hand side in one, or you have free space on the right hand side on the other one, the rest of the properties are the same. So the boundaries are the same. Assuming this is what's called the Born-von Karman. So Born-von Karman boundary conditions. So assuming that this is true for all three directions, so we could move from left to right, or from bottom to top, or from up to down, or whatever, we basically have these equivalents in all three directions. So the boundary, the two boundaries of a crystal are equivalent in terms of the wave function. The wave function should look the same in the left boundary than in the right boundary. Okay, so if this is the case, and the wave function is what we said it was in the previous slide, what we obtain is that psi of so n k, you remember this other notation we were using, of r plus n I a I is going to be e to the I n I k dot a I times the wave function n k of r. This is just what we demonstrated in the previous slide. but applying it to this particular case, the vector, the integer translation that takes us from one edge to the other opposite edge of the real crystal. Okay, and since these two have to be equal because of what we assumed in the previous line, this means that this here must be 1. Okay, and this implies that then e to the I n1 2 pi psi 1 has to be equal to 1. Okay, great. So from these we obtain that psi I, these psi i's that we said we could define as the exponent or part of the exponent of this exponential, which was the way we decided to write the values and eigenvalues of the unit translations, will have to be, let's see, equal to mi divided by n I. Okay, where mi would have to be equal to 1 or 2 or up to n I. Okay, let's see. Let's see what this is saying. So in order to have these equal to 1, then the psi I will have to be basically this, an integer number divided by this in such a way that when you have an integer number here divided by n1 multiplied by n1, the n1s cancel each other, and what you end up is an integer number multiplied by 2 pi I, which is effectively 1. Okay, so from these we obtain that psi I, and therefore this k vector that appeared also in the previous slide, this k vector here, can only obtain a finite, very large, but a finite number of possible values. Okay, so what this means is that this k will also be a sort of label of the quantum states that we already have. And it's actually not going to be one label, it's actually going to be 3 labels, because you have kx, ky, and kz, plus the n that we haven't said where it comes from, and it's actually not so important at the moment. So this means that our wave functions now will have 4 labels: the n and xy, kx, ky, and kz, which will now have only a finite number of possible values. So all the wave functions will now have an organized way of labeling. Just the same as it was, for example, for the hydrogen atom. In the hydrogen atom, we have the principal number n, we have the angular momentum, orbital angular momentum, L, the set projection of the angular momentum, which was m, and we have all these 3 numbers that have only a reduced number of possible values. So they have actually a finite, except for n. These 2 were constrained to be smaller than this one, and so on. There were a series of constrictions there that gave us all the states and all the possible labels for the different energy states and the possible energy values and energy states of the hydrogen atom. In this case, we will also have something similar, but in the case of a solid, instead of being n, l, and m, it's going to be n, kx, ky, and kz, the labels of the quantum state. Apart from that, these kx, ky, and kz, they do have some sort of physical meaning. We will discuss this in much more detail in the next session, but I don't want to leave today without pointing this out. This k will have to be then of the form m1 divided by n1 times a1 plus m2 divided by n2 a2 plus m3 divided by n3 a3. And the nice thing about this is that we now know that the a1, a2, and a3 will have to be vectors. As I said earlier, they're called the reciprocal vectors, and they are new vectors that form a new lattice, which is related to the initial one, but it's not the same, and are such that a1 is orthogonal both to a2 and a3. Okay, a2 is also orthogonal to a1 and a3, and a3 is orthogonal to a2 and a1. Okay, so all these vectors now can be constructed in such a way that the dot product between the reciprocal vectors and the original primitive vectors are at least orthogonal to the initial ones. In the case of a square lattice, capital A1 and small a1 are in the same direction. A2 and A2 and A3 and A3 are all in the same direction, but in other cases that is not always the case. And also the magnitudes are such that when you do the dot product between, let's say, A1 and capital A1, a 2 pi factor comes in. So I'm not going to go into the details, but you can check the Wikipedia entry on reciprocal lattice. It's actually very well written, it's very well explained there, and I ask you to have a look at that so that we keep the session a little bit shorter and that we can move on to the quantum mechanical aspects. The really interesting thing is now that let's not look into the n. You remember we had our function psi sub n k, which we could write as e to the I k dot r times u sub n of sub k of r, with this function being periodic with the same periodicity as the potential, and these being this first function being a plane wave. The interesting thing is, as I mentioned earlier, is that now the k vector can only acquire a finite, very large but finite number of states, and n is just a number that runs from 1 to infinity, and I'm not going to go into the details of what n is today, but we will more or less explain it in the next session. The interesting thing is the number of possible values that k can acquire are actually not just a finite number, but is the same number of atoms that there are in the actual crystal. So if you have a crystal that has Avogadro's number, let's say 6 times 10 to the 23 atoms, the number of possible k vector combinations, or the number of values that the k vector can acquire, is also 6 times 10 to the 23. So although finite, is a very, very big number. From here, we should notice a few things. Okay, if you remember from a previous slide, we had that k, the k vector, was m1 divided by n1 a1 plus m2 divided by n2 a2 plus plus m3 divided by n3 a3, and we also had the constraint that the mi's, all three m's, had to be equal to 1, 2, n I. So as I said, these are all the possible values that the k vector can acquire, and the other interesting thing is that this constraint basically means that the k vector has to live in what we call the reciprocal space, because it's written in terms of the capital A1, capital A2, capital A3, which is another space in which the A vectors are also the base of a new lattice, which we call the reciprocal lattice. Now, I'll draw here, just for the sake of the argument, let's assume this is infinite, sorry, no, this is, yeah, it's the reciprocal lattice, which is infinite, but we look into, let's say, we put the origin here, and we look into this. Let's assume that we put the origin here, so that's 0, and we look into only the unit cell that is around the origin in the reciprocal space. This means, this expression here means that the k vectors will have to be all in this unit cell that is close to the origin, that we call, actually this one has a special number, we call the first Bravais zone. Okay, this unit cell of the reciprocal space that is around the origin is what we call the first Bravais zone. So I'll just redraw it here. I'll just put here the first Bravais zone. So this is a zoom into that one if you want. And what we said is that the k vector has to be within this first Bravais zone. And this, what this means is that we will slice the first Bravais zone into many little pieces. Okay, so how many? Well, the number of pieces in this direction is going to be n1. Also in the other direction, here we will have n2. And of course, if we do it in the three-dimensional space, then we will have also n3 in the other direction. And all the intersections of these lines that I drew there, for example, this one, or this one, or this one, or this one, or this one, they form something that is also very similar to the reciprocal lattice. Is more or less a shrunk and finite version of the reciprocal lattice that has a finite number of divisions within the first Bravais zone. So within the unit cell of the reciprocal space, we have this very superfine yet finite network of points, network of points, which are the possible values that the k vector can acquire. Okay, so only these ones and only these ones are the possible values that the k vector will be able to acquire. So this one, this one, this one, this one, and so on and so forth. So, but not others. So all the little spaces here in, let's say, you can acquire these and these and these and these value, but not the values that are here in between. So all the values here in this area, you cannot, the k vector cannot acquire those values. Okay, so this is a three-dimensional block of space that more or less encloses all the possible values that the k vector can acquire, which in turn label each one of the energy states of the periodic Hamiltonian. So what we have here is a geometrical representation of in an abstract space that is called the reciprocal space, that within a finite volume gives you all a three-dimensional arrangement of all the possible values that the k vector can acquire, and therefore the possible values that this k vector that defines the plane wave of the wave function can take. Okay, so what does this mean? Coming back to the wave function, the wave function is going. Well, we already know psi sub n k will have the form e to the I k dot r times u sub n k of r, where u is again a function with the periodicity of the lattice. And basically, if you realize this u function is actually rather boring. So you remember the potential that we drew with all the lattice centers. So you have the nuclei lying somewhere around there. The yellow curve will be the potential, and essentially these u function here will be something that we don't really know the shape, but it's a shape that is not, first of all, is not changing, and second of all, it could be just a sine wave or something similar that has the periodicity of the lattice. So if you have a crystal, there will be part of the wave function of an electron in this crystal will be a function that has the same periodicity of the lattice, but that actually does not produce anything interesting. It's just like a standing wave there, or something that is standing there, has a shape with the periodicity of a potential, but there's nothing interesting about this. However, this part, this one really is the part where you have a plane wave. And a plane wave is something that is propagating, and is propagating in the direction defined by k. So k defines the direction and also the wave number that characterizes a propagating plane wave, a wave that propagates through the crystal. Okay? And that's actually very interesting, because that is, if you want to give it an intuitive meaning, that would be the electron propagating. Electrons, you know, they are particles, but they are also waves. And in the case of an electron in this periodic potential, the electron propagating will be basically represented by this plane wave. So this plane wave is this electron that is moving in the direction defined by the k vector, and with a wavelength or an energy or whatever you want to call it, that also is related to the magnitude of this k vector. So that being said, if we make an analogy between the k vector, and if we think of a freely propagating wave, not in a crystal, just in free space, and if this was a wave particle and so on, then k would basically be related to the momentum according to de Broglie, right? So the momentum P should be, again, be very careful because what I'm about to say, it's actually, strictly speaking, is wrong. The momentum is h bar multiplied by k. Okay, so in principle, if we know that or if we give the electron these, we use this plane wave and we understand it as the electron propagating through the lattice, then the momentum of this electron should be h bar times k, which again, this is strictly speaking not correct. And there are several reasons why this is not correct, but the most important one is k is a label related to the solution, to the eigenfunction of the Hamiltonian. Therefore, we can know k. We need to know k in order to know the wave function of an eigenstate of the energy. And the energy does not commute with the momentum, and we already know that. And therefore, k times h bar cannot be the momentum because we cannot know the momentum and the energy simultaneously. However, we can always define a new number that is k times h, because k we do know, and if we interpret the plane wave as the electron moving, again, it's just a loose, intuitive interpretation, but for the time being, let's say that's good enough. So if this plane wave is the electron moving, then h bar times k should be its momentum. But since formally we cannot say its momentum because it then would commute with, we would know the momentum and the energy simultaneously, then we give it a new number, and this is the lattice momentum. It's a new number. Intuitively is exactly the same as the momentum. It is, if we're not very formal and we take aside at the moment this problem with the commutation of the momentum and the energy, it is intuitively what we understand by the momentum of this electron propagating through the lattice. And we will discuss a lot more on the physical meaning of this lattice momentum, which we will just loosely call the momentum in the coming session. But now I just want to go back to one of the loose ends of our story so far. So if you substitute this wave function in the Schrödinger equation, since we already know this part as function of the position, what we obtain is now an equation for u, which is this part we haven't discussed very much. And if we do that, what we obtain is that the Schrödinger, when we substitute this in the Schrödinger equation, it will bring us to a new differential equation for u. And this differential equation will be h bar squared over 2m divided by minus I, the plus and plus vector k squared plus u of r, u applied on u, on this function that we want to find right now, and this should be equal to the energy, which we denote by a curly E times U. Okay, and this is not exactly a Schrödinger equation, but it's also a differential equation. And since we've already restricted this to be, U has to be defined in a finite domain, because we already spoke about finite crystals with finite dimensions. We don't really know what U should be unless we define the periodic potential. But what we do know is that this is a what we call eigenvalue problem in a finite domain. And if this is the case, we know that we will have a discrete number of solutions, and that is why the U has to have an n index, because it will have a finite, sorry, not a finite, but a discrete number of solutions. So we can always label them n equals 1, 2, 3, etc., etc., etc. And it of course is dependent on k. So this will have to be the case, and therefore that's where this n equals 1, 2, 3, and 4 index comes from. And it's just an argument of differential equations. So if we have a differential equation such as this one, the solution has to have a discrete number of solutions. We will not talk too much about the meaning of this n right now. We will discuss it. We will discuss the physics that it represents in the coming session. But I just wanted to point this out. And of course, this energy, of course, has a dependence on k. So the energy will also have a dependence on k, and also it corresponds. You will have an n for each one of the solutions of U. So the energy will have also the labels n and k, just the same as the wave function. And we will denote it in this fashion, and we will try to make sense of what this number means, or this function of k means, in the coming sessions. But for today, I would just want to leave it here. I just want to summarize very quickly what we achieved. What we did is we demonstrated the Bloch's theorem, which tells us what is the general form of the solution of a Hamiltonian under a periodic potential. From there, we worked out that it has to be a plane wave times a function that has the same periodicity as the original potential. We introduced the Born-von Karman boundary conditions, which just state the equivalence of the wave function in the borders of the lattice. So this is introducing a more realistic case in which the lattice is no longer an infinite number of points in all directions, but more a finite number of sites, which resemble much more a crystal. From there, we obtained the idea of the reciprocal lattice, and we obtained not just the reciprocal lattice, we realized that all the values of k will have to be in a confined region of the reciprocal space, and that this finite region we called the first Brillouin zone. And not only that, the only possible values that the k vector can acquire are on a fine cut mesh of this first Brillouin zone, which are the only possible values of the k vector, which is also the three labels that, 3 out of the 4 labels that label the wave function. And finally, we introduced this notion of lattice momentum, which is basically this k vector that at the moment is still something relatively abstract and is something that lives in the reciprocal space, but that does have a little bit of physical intuitive meaning in terms of representing the moving electron in a lattice as this plane wave part of the wave function. So I want to leave it there, and hopefully next time we will you will join me again, and then we will give much more physical meaning, and the next session is going to be much more in terms of trying to understand and give physical meaning to all these things that we've done today. So thank you very, very much for being here with me, and I hope to see you next time.